Before we were talking about interest formulas, and now we're going to talk about exponential growth in a more general sense. Before when we were talking about interest formulas, we derived a formula for interest compounded continuously, which really was exponential growth. And so we're going to look at that in a more general sense. So we're going to look at exponential growth and the opposite. We're going to look at decay too, exponential decay. So the formula we're going to use is very similar to what we had for our interest formula. We're going to have a final a, we're going to have an initial a, and e raised to the power of kt. And in this case, k is going to be our growth rate. And k is going to be related to the time we use. Now we're not always going to be using time in years now. Time may be any general time. It could be days, it could be weeks, it could be years, it could be any sort of time. A0 again was, just like before, is our initial condition, our initial state. And A of t is our final result. So let's just jump right into an example here, since we've already done these sorts of things before. And let's talk about, in our example, let's investigate the growth of a bacteria culture. And say we're interested in, say we have 3 grams of this stuff, and we want to know how much is left, or how much there is after 3 days. If we know the bacteria, this particular bacteria doubles in size every 2 hours. Okay, so that's our problem statement. We need to get to work coming up with a plan to solve this. Well, when you get a problem statement like this, and of course it's assumed here there's unrestricted growth occurring, and that often is stated in the problem. It wasn't stated here, but I'm saying it now. Let's just write our exponential growth formula down and start putting in numbers. Okay, so we want to start with 3 grams. So to me that looks like A0. So we want to start with 3 grams. And it doesn't look like we have a growth rate, so I'm going to put K there. And we're going to let it grow for 3 days. But I'm going to convert that 3 days to hours, since I have information down here about how fast the bacteria doubles in hours. We need to keep our units the same, and since I have days and hours, I'm just going to choose hours here, so I'm going to go with 72. So we have that, and this equals our final amount of material after that time. Well, we see we can't solve this relationship because we have 2 unknowns. We have this K here, and we have this A of t here. We need to figure out what K is. So how do we approach that? Well, we can split this problem up into 2 parts. In part 1, we're going to look for K. Then we're going to stick K in there, and we're just going to type that into our calculator and figure out what A is. So how do we find K? Well, let's go back and look at our relationship again and see if we have any information that can lead us to K. A of t equals A0 e to the kt. Well, we know that in 2 days, or in 2 hours, we know that in 2 hours, this thing doubles. Well, if it doubles, that means that our final amount equals twice our initial amount. So our final amount divided by our initial amount equals 2. Well, it looks like we can deal with these two unknowns in this way, in this relationship, in our search for K. We get A of t over A0 equals 2 equals now e to the k times 2. So solving this relationship is something we can do. We have a k there. Anytime we have a value trapped in the exponent, what's the best thing to do? Best thing to do is to natural log both sides. Since this is base e, we can take log base e, which is natural log of both sides. Natural log of 2 equals natural log of e to the k times 2. And natural log of 2 is a number here. We can just get that out of our calculator. Natural log of e to the k2, using our properties, this is log base e to the base e raised to the k times 2 power. That means that we can pull this directly out of the exponent, and all that disappears, and this equals natural log of 2. So, and I'm reversing sides here, k equals natural log of 2 over 2. Very common expression, natural log of 2 over some time value, in this case 2 hours. And if I calculate that with my calculator, I end up with 0.3466. And why did I do that? I did that. I found K, so I can stick K now into this relationship. And we have all the values in that relationship. So in part 2 now, we're going to solve for A of t. So A of t equals A0 e to the k t. You can look back at the problem statement. You're going to see that A0 was, let me see, I think it was 3 grams. So I'm going to put 3 here, leave off the grams. E to the k, 0.3466, very high growth rate. And the time was 3 days, but remember, we calculated K using hours. So if this was hours, then we got to stick with hours down here, and we've got to go 72. It's 24 times 3. 24 hours times 3. Okay, I calculate all this, and if you put this in your calculator, you're going to end up with 250,813,369 grams, which is a lot of material. So if you let this thing grow in an unrestricted fashion, that means you're feeding it properly. You're not constraining it with space or anything like that. You're just letting it explode. That's how much it's gonna produce over time, and I think that's somewhere around 230,000 tons of material. So the idea of unrestricted growth in that fashion is probably a little unrealistic, but if it could happen, that's how it would work. Okay, now we're going to look at decay in our next video.